Hello students, welcome you all for DSP lecture videos. In this class, we can discuss the design of Butterworth filters using bilinear transformation. Before starting the actual problem of bilinear transformation, let us recall the previous problem, that is Butterworth filter. The design procedure remains same except last step. Okay. So what is the steps followed for designing of low pass Butterworth filter is step 1. We are finding the order of the filter, that is n, and if the n is not an integer value, round off the next higher integer value for order of the filter n. That is your step 1. Step 2, to find the cutoff frequency omega c, which is nothing but omega c1 plus omega c2 divided by 2. That is step 2. What is step 3? In step 3, we are finding the normalized transfer function Hn of s, which is nothing but 1 upon product of left of poles of s minus sk. How we are calculating a Butterworth polynomials? We know that it depends on the value of n. If n is equal to odd number or n is equal to even number, so based on the condition, we can calculate the Butterworth polynomials sk. Okay, and we are finding Hn of s, that is your normalized system transfer function Hn of s. Once we calculated Hn of s, the last step is to calculate the analog system transfer function Ha of s. It is known as low pass to low pass transformation. Low pass to low pass transformation. Here we obtained Ha of s, where substituting your Hn of s by s is replaced by s by omega c and obtain the actual analog system transfer function Ha of s. This is the procedure we discussed in the previous problem. In this problem, until step 4 it is remain same. Until step 4 it is remain same. Okay. Only extra thing is in step 5 we have to convert whatever your analog system transfer function H of s is. We have to convert this analog system transfer function to digital transfer function H of z by using bilinear transformation. Bilinear transformation as well as impulse invariant transformation. These two techniques can be used generally to convert your analog system transfer function H of s to digital system transfer function H of 2. These are the two effective methods used in general to convert your H of s to H of z. In this problem, I am using bilinear transformation and I will show how you convert your H of s to H of z by using bilinear transformation. Let us start the problem. The problem goes like this. Design and realize a digital low pass filter using bilinear transformation to meet the following specifications: monotonic stop band and pass band, minus 3 dB cutoff at 0.5 pi radians and minus 15 dB attenuation at 0.75 pi radians, and verify and assume t is equal to 1 second. Generally, they will give the time period t. The time period t is not mentioned in the problem. In bilinear transformation, you can assume generally the default value of time is 1 second. Here also, it is not clearly given, so that's why I am assuming t is equal to 1 second. This you have to remember, because when we convert your H of s to H of z, we required time, okay, sampling time t, which is 1 second. Now I am assuming here. Generally they will mention 2 seconds, 5 seconds or 3 seconds like that. If it is not clearly mentioned in the problem, assume t is equal to 1 second. Next, later on that I will go to the frequency specifications. You can observe here it is a bilinear transformation. It is a bilinear transformation. Okay, the given specifications are digital filter specifications. The given filter specifications are digital filter specifications, and we are not supposed to design directly the digital filter specifications. So as we know already, we are always designing the field low pass Butterworth filter in analog, and then convert your analog filter specifications to corresponding digital filter specifications. Now whatever gain, it is same whether it is analog and digital, the gain remains same, but the frequency will vary. If the given frequency is analog or digital, we can observe here based on the problem given. Here bilinear transformation, automatically the frequency is given is digital. So generally that's why I will give the note here. If the type of frequency omega or digital analog or digital frequency omega W is not specified, we can consider it as digital frequency. Now we cannot use directly digital frequency, as we know we are not directly design any digital filter design directly. Hence we are converting this digital frequency into corresponding analog frequency. How we are doing that, I will show here. So from the digital specification W, how you get your analog specifications, you can observe your omega 1 is equal to 2 by t into tan of omega 1 by 2. Similarly, omega 2 is equal to 2 by t into tan of omega 2 by 2. Substitute here, assuming t is equal to 1 second. So substitute that. So 2 by 1 into tan of, what is your W1? W1 is given clearly 0.5 pi. So 0.5 pi by 2 radian per second. So therefore we are getting 2 radian per second approximately. Similarly, calculating omega 2, generally I will take omega 1 and omega 2 are normal frequencies in analog, but here we are converting from digital to analog. That's why I will take omega 1 star or omega p star. So because we are converting from digital to analog, so that's why we will take it as star. Similarly, omega 2 star is 2 by t into tan of omega 2 by 2. So omega 2 is 0.75 pi by 2, you will get 4.828 per radian per second. Now what we did here is convert the given specification which is digital in nature. So those digital frequencies are converting to corresponding analog frequencies. As we discussed many a times, we are not directly design any digital filters. So we design analog filter and using the techniques, frequency transformation techniques, to convert your analog system transfer function to digital system transfer function h of z. Now once we do that, so you get all the specifications which are related to analog. Now you can start the actual filter design. Now you can mark all these specifications what we obtained, revised specifications, in the magnitude squared response. K1, K2, omega 1 and omega 2, and we can go with the next step. What is the next step? In next step, step 1, that is we are calculating the order of the filter n. So what is the formula for n to find the order of the filter? N is equal to log to the base 10 of 10 to the power of minus kp by 10 minus 1 divided by 10 to the power of minus ks by 10 minus 1 whole divided by 2 log to the base 10 of omega p by omega s. Here 10 if it is not mentioned, it is a base 10 by default. Now substituting the values of kp, ks, omega p and omega s. So this is omega p star, actually this is also omega s star. Omega p is nothing but omega p star and omega s is nothing but omega s star. So once we do that, substitute, I am getting n value as 2. Once we are getting n value is equal to 2, we already know that how to calculate the cutoff frequency omega c in the step 2. So let us go to the next step. Step 2, that is calculating the cutoff frequency omega c. Now in omega c can be calculated by omega c1 and omega c2. So therefore what is omega c1? Omega p star divided by 10 to the power of minus kp by 10 minus 1 whole power 1 by 2n, and omega c2 is equal to omega 2 divided by 10 to the power of minus ks by 10 minus 1 whole power 1 by 2n. Substitute omega p kp here, and you are getting omega c1 as 2 radian per second and omega c2 as 2.03 radian per second. You take the average of this 2 for cutoff frequency omega c. Omega c is equal to omega c1 plus omega c2 by 2. So you can substitute 2 plus 2.03 by 2, you will get omega c as 2 radian per second is the answer. So once you calculate step 2, we know step 3. Step 3 is to calculate the normalized system transfer function Hn of s. As we know here, n is equal to 2, so we will get H2 of s. H2 of s is nothing but normalized system transfer function. Okay, how to do that? We know Hn of s is equal to 1 upon product of left of poles of s minus sk, or this s minus sk is called as Bn of s, which is nothing but Butterworth polynomials. Butterworth normalized Butterworth polynomials. Okay, it is known as Butterworth polynomial. Okay, Butterworth polynomial. So here n is equal to 2, we are getting 4 poles, and we have to choose 2 poles which are located at left of, and as we know here n is equal to 2, the procedure is different for finding the order of the filter or to find the Butterworth polynomials, whereas n is equal to even, the procedure again remains same. Here n is equal to 2, how to calculate the poles sk? So sk is equal to 1 at an angle of 1 pi by 2n plus pi k by n. So we will get k is equal to 0, 1 up to 2n minus 1, n is 2, so 4 minus 1 is 3, so k is equal to 0 to 3, you will get 4 poles. Out of 4 poles, 2 poles are located at left half of the S plane, and remaining 2 poles are located at right half of the S plane. Now put k is equal to 0, 1, 2, 3, you will get the values of poles. S naught is 1 at an angle of pi by 4, it is 45 degree. 45 degree is located right half. Similarly, when S1 is equal to 1 at an angle of 3 pi by 4, which is 135 degree, located at left half of the S plane. Similarly, S2 is also located at the left half of the S plane, whereas your S3 located at the right half of the S plane. Okay, out of 4 poles, S0 and S3 are the poles which are located at right half of the S plane. So hence these poles are negated, whereas S1 and S2 are located at left half of the S plane. We'll consider these poles. Okay, so let us look at here. Your S0 and S3 are the poles which are located at right half of the S plane, whereas S1 and S2 are located at the left half. These 2 poles are neglected or discarded. So next, so once you do that, you know the value of S1 and S2. So what is your S1? S1 value is 3 pi by 4, 3 pi by 4. So you will get cos 3 pi by 4 plus j sin 3 pi by 4. You will get cos is second quadrant negative, sin is positive. So you will get minus and plus values. So minus 0.707 plus j 0.707. Whereas your S2 is third quadrant both are negative. S1 and S2 should be negative. You write those value, you will get the poles. So once you get this, simplify the poles, you will get S square plus 1 plus 4.414 2 into S plus 1, or it can also be written as H2 of S is equal to 1 divided by S square plus root 2S plus 1. This is also the transfer function for n is equal to 2. Once you get this, we go to next slide. We have to calculate the normalized transfer function to system transfer function Hn of s. So what is your Hn of s? Hn of s is equal to He of s, where s is replaced by s by omega c. So here omega c is equal to 2 radian per second. So therefore H2 of s is equal to He of s, where s is replaced by s by omega c. So omega c value is 2 here, it is clearly mentioned. So substitute, okay, s square plus root 2s, s is nothing but s by 2 plus 1, take LCM as 4, you get 2s square, 2s square plus root 2s plus 4. So this is the analog system transfer function h of s. You can stop up to this point whenever they will ask only low pass filter design, that too analog. If they are clearly mentioned in the problem, if it is digital filter, again you have to go to one more step, that is we have to derive h of z from h of s. What is your h of s? H of s is the system transfer function obtained, okay, and whereas h of z is, again it is also a system transfer function obtained by using bilinear transformation. So how to do that? H of s is equal to, to find h of z by using bilinear transformation, h of z is equal to h of s, where s is replaced by 2 by t into 1 minus z inverse divided by 1 plus z inverse. The value of t is equal to 1 second. So wherever s is there, replace that 2 by t into 1 minus z inverse by 1 plus z inverse. So therefore I will get 4 divided by 2s. So 2 into t is value 1. So 1 minus z inverse by 1 plus z inverse whole square plus 2 root 2 into s. S is nothing but 2 into 1 minus z inverse by 1 plus z inverse, because t value is 1, 2 by 1 is 2 only, plus 4. Okay. So you take the LCM, 1 plus z inverse whole square as an LCM, you will get, okay. So 4 into 1 plus z inverse whole square divided by 4 into 1 minus z inverse whole square plus 4 root 2 into 1 minus z inverse by 1 plus z inverse. So you will take the LCM. So you will get 4 into 1 minus z inverse plus 4 root 2 1 minus z inverse into 1 plus z inverse plus 4 into 1 plus z inverse whole square. So this is in the form of a minus b whole square. This is in the form of a plus b whole square. This is in the form of a minus b whole square, a plus b whole square. So this is a minus b into a plus b. So simplify, you will get 4 into 1 plus z power minus 2 divided by 0.586 z inverse z power minus 2 plus 3.4142. This is the equation for h of z. We can take LCM, simplify, you will get h of z, which is the actual system transfer function, which is in digital domain or z domain. With this, I will conclude my today's class.